Okay, YouTube, this is my second video in my module on inconsistent systems as well as dependent systems. But recall that in the last video we had looked at some inconsistent systems or systems of equations such as this one right here that had no solutions. And in this video what we're going to do is we're going to focus on something that's a little bit different, but a situation where the system would actually have infinitely many solutions and we actually have to name them all, which is going to make this a little bit more difficult than inconsistent systems. So I guess what I mean is when we express the answer to an inconsistent system, we can go straight up and say just no solutions. But when we express the answer to something like this that's going to be a consistent system but consistent dependent, where there's infinitely many solutions, we're going to have to express it in a kind of a special way in order to give all infinitely many solutions to the system. So let's go ahead and start with this. We've seen that, with systems of three equations and three variables like this, or at least in the last video I discussed how really what it is if we were to graph these, all of the solutions to each graph, okay, would represent themselves as a plane, a two-dimensional plane, and it's not curved, so it'd be a linear plane. But basically, what we're looking for is all of the points that are solutions to all three equations at the same time. And graphically speaking, we're saying that these are all the points of intersection of all three planes, or where they all coincide. And so when we look at systems that have infinitely many solutions, graphically speaking, one way to look at this is maybe we have three planes that all intersect along all of these lines right here. And so you can see, or all of these points right here. So you can see that really they intersect along this entire line, and we could say that the set of points along this line right here are the solutions to the system. And the interesting thing is, what if we have three planes here, kind of like this picture down here, that all coincide? Then we could say that the set of points here, all of them, are all of the points that all three equations have in common at the same time. So they are solutions to the system. And so since we're looking for points of intersection, we're really looking for all of these points that they coincide at, and we're going to have to list them all. So let's go ahead and take a look at how we might use Gaussian elimination and augmented matrices in order to determine whether the system is, consistent, dependent or not, and then also listing all infinitely many solutions to this system. So let's go and start with this. We would want to write, an augmented matrix for the system to begin with. And so our first equation here, or our first row of the matrix, would be 3, -4, 4, and 7. Okay, so we would say it has 3 rows, 4 columns. We could say it looks like our second row is 1, -1, -2, and 2. And then our third row is 2, -3, 6, and 5. And so the first thing we want to do is get a 1 in the top left corner. So now one way we can do this is we could take everything in the first row times the reciprocal of this leading thing, which is a 3. So if we took everything times a third, it would make it a 1. But I see that we already have a 1 here in the second row. And so for me, it just seems to me to be a lot more convenient to just go ahead and say what we're going to do is then we'll just go ahead and switch row 1 and row 2 around. So we say row 1, switcheroo with row 2. That's what we want to do. And so now we have a 1 in the top left corner. I'm just going to rewrite row 2 or row 1 used to be here. And I'm going to rewrite row 1 where row 2 used to be. But essentially we'd say that this new row equivalent matrix has the same solutions as the original system. So let's take a look at now using this 1 to get the entries below it to be zeros. And so the neat thing about that is we can always just take the 1 and multiply it by the opposite of the numbers we're trying to cancel out and add them to these numbers. So in other words, we will, to cancel out this positive 3 here, we'll take row 1. So we'd say take row 1 times a -3 and add that to row 2. And then what we'll do is we'll take row 1 times a -2, which is the opposite of 2, and we'll add that on to row 3 here. And so our new row equivalent matrix will be a 1, -1, -2, and a 2 in the first row. Now our second row and our third row have to start with zeros now because of these two row operations. Well, let's go ahead and work on one row at a time. Our second row, we say -3 times this -1 would be a 3, and 3 plus a -4 is a -1. -3 times a -2 is a 6, and 6 plus a 4 is 10. We'd say -3 times a positive 2 is -6, and -6 plus 7 is a 1. Now our third row, -2. -2 times this -1 is a 2, and 2 plus a -3 is a -1. -2 here times this -2 is a positive 4, and 4 plus 6 here is a 10. But you see what happens here. We get a -2 times this positive 2 up here, which is a -4. A -4 plus a 5 is a 1. And so already what I want to point out to you is that these are identical. Okay, identical. And so this is a good indicator of dependency. And dependency Okay, we're going to find out means infinitely many solutions, but it also means that these two equations are basically dependent upon one another. One is the other equation. And so because essentially they are the same equation, what's going to happen here now is this. If we were to continue our Gaussian elimination, we would want to get a positive 1 here. So we would take a negative 1 times row 2. Let's go ahead and rewrite our whole matrix here. We have 1, negative 1, negative 2, and 2. Our second equation would be the opposite, 0, positive 1, negative 10, and negative 1, and then we would say 0, negative 1, positive 10, positive 1. And so now from here we would see that using this 1 right here, we could basically multiply it by the opposite of the thing below it and add it to the thing below it to get that to be a 0. In other words, it already is the opposite of the thing below it. So we could say, basically, we'll take row 2 times a 1 and add that to row 3. In other words, we'll add row 2 plus row 3. So we would get this here. We get 1, negative 1, negative 2, and then we would get a 2. We would get a 0, 1, negative 10, and negative 1. Now, adding row 2 to row 3 here, we get 0 plus 0, 0. 1 plus a negative 1. We should have expected a 0 there after this row operation. But look what happens to these last two entries here and here. We get a negative 10 plus a positive 10 is a 0, and a negative 1 plus a positive 1 is a 0. And so something really interesting happens here. As a matter of fact, we want to point this out. It is just that if we were to rewrite the system, the system associated with this augmented matrix, then we would say that this x, y, z, and constant would be 1x minus 1y minus 2z's equaling a 2. Our second equation would be y minus a 10z equals a negative 1, but our last equation would really say 0 equals 0. And so one thing that I want to kind of point out here about this is that it's always true. When's it true? Always true. So what this means is that we have a system that's consistent, and that just basically means we get at least one answer, but the word we're going for here is dependent. Okay, and dependent basically means that we have infinitely many solutions, infinitely many. And so you would think that we get to be done at this point. Kind of like with inconsistent systems, we just say inconsistent, done, we're done with it. Something like this here, what I want you to understand is this is the same as, okay, let's draw a little arrow here. The same as x minus y minus 2z equals 2, and y minus 10z equals negative 1. These two systems, that is to say, if we were to just ditch this right here, these two systems would essentially be the same thing. And so what you can really see is that we have, if we were to graph this, a plane, maybe here's my plane, and another plane. Maybe this plane cuts across this way, like that. But what you could see is maybe these two planes intersect along every point, maybe along this line. And so it's not so much that I want to graph them and represent them visually, but I do want to visually say, well, if you've only got two planes, then the only possible instance is that they either intersect along a whole line or they don't intersect at all. And these obviously intersect because we didn't get inconsistent. So here comes the part where we're going to write our solutions to the system. So writing the solutions to this system, okay, let's write a set of steps here. Basically, what we're going to do is this. We're going to talk about dependent system solutions. The first thing we're going to do is choose a variable to represent with a parameter. Choose a variable to represent with a parameter. Now, a parameter is just another variable here. Represent with the variable a. So let's just go ahead and say we're going to agree upon it that we're going to use a. And so essentially, I'm going to write a note here. This is typically we allow z to equal a. And so what we're going to do with this system right here, essentially this is the same system that we ended up with right here, but I'm going to say it's the same as this one right here. We're going to say let z equal a. Boom. So what this is going to do for us essentially is right off the bat, we're going to say then our solution. Okay, with respect to our solution, we have some points of intersection, and we know that the z value here is equal to a. That is to say that we already have 1/3 of our answer here. The only two parts that we're missing here, we have z, we don't have x, and we don't have y that we need to go find. But because we already know that we're allowing z to be equal to a, just like if I were to say, well, what if z was equal to 2? What would I do then? What I would do is that I would go back and I would put it in this equation right here. And so what we're going to do is we're going to say, well, if y minus 10z is equal to a negative 1, and we know that z is equal to a, then what we really get here is this. In solving for y, we would say, well, I would add 10a to both sides of this equation. Essentially what we would get is this idea that y would be equal to 10a minus 1. Now I'm going to put parentheses around that, but down here in my solution I'm going to say basically 10a minus 1 is our y value if your z value is equal to a. I'll even put a box around this. Okay, we should put a box around this and around that. So now we know we know y and we know z in terms of a. What we're going to do is we're going to go back and find x in terms of a here as well. So we're going to say x minus y minus 2 times z is equal to 2, where z is equal to a. We said y in terms of a is 10a minus 1. And what we're going to do is we're going to solve for x here in terms of a. So first thing I want to do is simplify. Now because I have a negative in front of the set of parentheses here, really this is going to become x minus 10a but plus a 1. Here we get minus 2 more a's equal to 2. And when we combine these total a's together, we get x looks like minus 12a plus 1 equals 2. So here's the trick. We're going to get x by itself by adding 12a and subtracting 1 from both sides. So add 12a minus 1. But what we turn up with is x then is equal to, I suppose on the right side, 12a, and then a positive 2 and a negative 1 would give us a positive 1 here. So I'm going to put a box around this right here. We say 12a plus 1. 12a plus 1. So 12a plus 1. These are going to be the solutions to our system right here. And so just to fill in the steps here, basically I said choose a variable to represent with the variable a. And typically we allow z to equal a. But then what we do is we basically back solve using our designated variable value. Let's try that again. I can do better than that. Designated variable value. And then 3, basically we're going to write an ordered triple in terms of our selected variable. In this case, it's a. So what I want to do is I want to look at basically doing this again, except for basically with a new example here. Sorry, I'm trying to get back to my main screen. Okay, so let's take a look at this. What I want you guys to try basically now is look at this dependent system. And I'll tell you right now it comes out to be dependent. Pause the video, see what you come up with Gaussian elimination, and see if your solutions match mine. Okay, so let's take a look at our solutions here. Our augmented matrix would be a 1, a negative 2, a negative 1. Draw our bar here as a 5. And so our second equation here, our second row in our matrix would be 2, negative 5, 3, and 6. Our last row would be 1, negative 3, 4, and 1. So because we're using Gaussian elimination, because I already have a 1 up here in the top left, what we're going to do is we're going to use that 1 to make everything below it into zeros. And so I know that when I do this, I'm not going to change row 1. As a matter of fact, I get a little happy there and I started writing it already. But basically, let's go ahead and say what we're going to use this 1 for. We're going to take 1 times a negative 2 to get rid of this positive 2. So we're going to say negative 2 times our row 1. We're going to add that to row 2. And we're going to take this positive 1 times a negative 1 to get rid of this positive 1. So we say negative 1 times row 1. We're going to add that onto row 3. And so what we get are zeros here by default. We cause this to happen. But looking at row 2, the rest of its entries, we'd say negative 2 times a negative 2 here is a 4, and 4 plus a negative 5 is a negative 1. Negative 2 times this negative 1 is a 2, and 2 plus 3 is a positive 5. If we were to say now negative 2 times this positive 5 is negative 10, and negative 10 plus a 6 is a negative 4. Now looking at the last row, negative 1 times row 1 plus row 3, we get negative 1 times a negative 2 is a 2, and 2 plus a negative 3 is a negative 1. Negative 1 times a positive 1 up here is well, 1. 1 plus 4 is a 5. And then looking at this, we say negative 1 times this negative 5, positive 5 is a negative 5. And if we were to add negative 5 plus this 1 here, we would get a negative 4. And so already what I want you to see is that these are identical. And what that's going to cause to happen is we're going to get a dependent system. But let's go ahead and carry out the rest of our Gaussian elimination Now that we have a 1 in the top left and zeros underneath, let's get a 1 in the main diagonal in the second row. So since we want this to be a positive 1, what we'll do is we'll take the whole second row times a negative 1. So negative 1 times row 2. So row 1 stays the same. Row 3 stays the same. 0, negative 1, 5, negative 4. But row 2 switches to the opposite value. So we have 0, positive 1, negative 5, and positive 4. And so now that we have a 1 here, let's use this 1 to get everything below it to be a 0. And so we'll take it times the opposite of the thing below it and add it to the thing below it. So the opposite of negative 1 is positive 1. We're going to take row 2 times a positive 1. We're going to add that on to row 3. So row 1 stays the same. We have 1, negative 2, negative 1, and 5. Row 2 is now the same since we have a 1 on our main diagonal there. And then we would say row 3 still has a 0 here, but we'd say 1 times 1 plus a negative 1. That'd be 1 plus negative 1 is 0. Should get a 0 there. But looking at these last two entries, we'd say, okay, well, negative 5 plus 5 is 0. And 4 plus a negative 4 is also a 0. And so really quickly, what we want to do is we want to make sure that we rewrite the system associated with this augmented matrix now that we have it in this form. And our system would look like this. We'd have x minus 2y. You should have a negative z here, and that's equal to a 5. Now your second equation should say y minus 5z equals 4. And then the last thing I'm going to do is I'm going to say that really this right here is 0 equals 0. And I just want to say this, I kind of just want to leave that separate, because what this does is it tells me, first of all, that I didn't get an inconsistent system, I got a consistent system, and that it's dependent. It's dependent, okay? Because we always have equality of 0 and 0 here, okay? Or two of these equations are really the same equation. Or another way to look at this is if we had two planes that were intersecting, here and here, they would intersect along this entire line of values right here. So we have to find all of these values. So what we're going to do is this. We're going to follow our steps from the last page. We're going to say, well, let's start with allowing, say, z in this case to equal a. So with respect to our solution, we want to write this really big here. Solutions in this case, we're going to say we already know that the z value is equal to this a right here. So now what we're going to do is find y and then backsolve to find x. So just like a normal problem, if you already knew what z was equal to, we would go plug it back into this second equation here for z. So in other words, we would get y minus 5z is equal to 4, where instead of a z here, we would have an a. So we get y minus 5a equals 4. And remember, what we're doing is we're solving for y. So if we add 5a to both sides of this equation, we really get y is equal to 5a plus 4. So I'm going to put a box around this. Okay, I'm also going to put it up here in my solution. We would say it's 5a plus 4 constants. Now we know y. And we did say we allow z to be equal to a. But essentially what we're going to do now is go plug these back into the first equation. The first equation here, I'll just rip it down here. We have x minus 2 times y minus a z is equal to a 5, where our z is a. Our y we were able to discover in terms of a as 5a plus 4. So what we're going to do is we're going to clean up the left side here. We get x, looks like we'd get minus 10a minus 8 minus an a is a 5. If we combine these two a values here, combine like terms, we would get negative 11a minus 8 is 5. Let me scroll down a little bit here. Okay, so now that we have this, essentially let's isolate x. Okay, so we're going to add 11 a's and add 8 constants to both sides, 11a plus 8. And what we end up with is this here. We get x then has to be equal to 11 a's, but 8 plus 5 here, that would give us a 13. So we would get, I'll box this here for us here, 11a plus 13 though is what we get. So 11a plus 13. So 11a plus 13. Okay, so we're going to put a big box around this. Okay, but those would represent all infinitely many points along this line here, but we're going to have to represent dependent systems using an ordered triple in terms of an added variable